Welcome to Bayesian Statistics, non-conjugate example. I'm going to call this revisit. We're going to go back and look at the example we just did across the last 3 videos. And what we're going to do is we're going to say what happens if we used a non-conjugate informative prior distribution where the prior distribution and the data contradict each other, okay? So if you haven't watched previous videos, you should probably go back and look at them. Otherwise, you're likely to be confused. Again, we're on the same example where we're interested in estimating the number of students who would want to participate in a debate on neoliberalism, okay? And the researcher knows that less than 10% of the students would want to do this because, let's face it, nobody likes to stand up and talk in front of people, okay? Now, what I did changed here, so this is the prior distribution from last time. I'm going to leave that the same because it's less than 10% of the students. Here, what if the data contradicts that? Okay, so she takes a survey of 253 students and finds that 33 would be interested in participating. And notice that this is more than 10% in the data. So the data says more than 10% would actually be interested. So how does this change things in our posterior distribution? Does things change a lot, a little bit, and whatnot? So let's go back through what we just did and change the likelihood. This is good because it gets you to see this idea of numerical integration again. So we're just going to go through the exact same steps we did in the last video. If you've got the code for it, you can just copy and paste it, and you'll see where you need to swap out a few numbers, and then it works just fine. Okay, so now our likelihood is p to the 33. Before it was p cubed. Now it's p to the 33, 1 minus p to the 220 instead of 250. So change a few little numbers in what we did before, and things will just pop right out for us. Okay, going to plug it into the posterior distribution. Now, this is what we have to integrate on the bottom. Notice it's very different than before. Would be nice if there was some easy way to transform between them, but there isn't. So we're just going to brute force through the numerical integration. We've created our function like before. Here we've swapped out our 3 with 33 and our 250 with 220, okay? And I put all of it together on one slide here. And I used delta x is 0.0001. So I plugged that in here. Our integration goes from 0 to 0.1. Again, we're multiplying the height, f of x, times the width, and then we're adding them up for each of the little rectangles, and this is the number we get out, okay? 7.51 times 10 to the negative 45. So this is a really small number. All right, we're going to run with this number. Turns out you can play with it, squeeze down 0.0001, add another 0 in there, and you end up with pretty much the same answer. So I'm going to say this is close enough. I plug it in here, and this is my posterior distribution now. It's different than my previous one, and you should expect it to be different because the data is different. Okay, so this is what we're going to work with. Here's what it looks like if I look at a picture. This looks very different than my last picture in the last video. Go back and look at it. You'll see this is a very different picture. Most of the probability is stacked up near 0.1. Before we had a nice curve over here, and it was very unlikely to be around 0.1. Now it's extremely likely to be around 0.1. Okay, so we're going to need the CDF just like before. So here I took the CDF function that I had before, swapped out my 2 numbers, divided by my new denominator that I came up with. And then again, I'm just going to use the cum sum function like before. Here I have the height, I have the width, and away we go. And this is what the CDF looks like. Now you're saying, wait a minute, this looks exactly like the PDF, but it doesn't, because if I come back, I'm going to roll back a few slides. This goes from 0 to over 100. This one goes from 0 to 1. It's a CDF. Has to go between 0 and 1. All right, so we would map this backwards. Go to 0.975, come over, go down, go to 0.0025, go over, go down, and that would give us our interval. Again, we can use our formula that we did before, and we get our interval here of 0.077 and 0.0997. And notice that entire interval is less than 0.1. Why? Because we told it has to be less than 0.1 in the prior distribution. So you can see the prior distribution really can influence the inferences that you come up with. Is that a good thing? Is that a bad thing? I don't know. It depends on the situation you're in and how certain you are that really less than 10% of the students would want to do this. So if the researcher is really certain of that, then this interval's a reasonable interval. All right, so what we're going to do in the next video is we're going to say, what if we did a conjugate distribution? And how would that change our inferences? But we're going to stay with exactly the same likelihood here so we can see how different a conjugate distribution posterior looks versus one where we used a non-conjugate distribution. So we'll wait till the next video for that, and I will see you there.